Hi everyone, in this video we will be controlling the brightness of an LED using a microcontroller and a variable resistor. So let's change our variable resistor here and our LED. You can turn it off or you can just adjust its brightness all the way up. Now let's have a look at our circuit. There's not much of a change from our previous blinky circuit, so we have our PIC10F220 here. And to GP0, we have a 220 ohm resistor connected as a current limiting resistor to our blue LED in this case. And we also have our pot, which is the variable resistor. And one of its pins, the first pin is connected to VDD, which is 5 volts in this case. And the ground is, and the third pin, the last pin is connected to the ground. And the second pin, the middle pin, is connected to GP1 pin on our microcontroller. So in this project, I'm just powering it through the PIC3, which is also being used to program the device. And if you have any problems with a PIC3 connection, check out my previous video, link in the description below. One thing that you need to be careful while you are programming this circuit and PIC3 is connected, because the ICSP clock pin is connected to GP1. And if you put your pot all the way down or all the way up, then you will be just grounding your programming clock or driving it high, and you won't be able to program your PIC. So you can remove the pot while you are programming, or you can just keep it somewhere in the middle. While programming, the PIC3 can still provide clock to the chip. So let's have a look at the code a little bit. Okay, so again, this is our previous code, but I polished it a bit, and now we have two different methods. Like the one function is pot control, which is the new one, and the other one is the pulsating glow. Again, I will just put the links to this code in the description below. So let's have a look at our pot control function first. So the first thing we do, as in our previous video, is to set our timer with a prescaler of 8, and that would give us roughly 976 hertz of frequency, which is more than good enough for driving an LED. And one of the significant bits of the option register is this 0, which is the which is to put the timer in timer mode, because it can also be in counter mode. And we have also assigned our prescaler to the timer, because in this PIC10F series, you can only assign the prescaler either to watchdog timer or timer 0. So trace bits are quite simple. Again, our GP0 is 0 because we're gonna use GP0 as the digital output, and GP1 is 1 because it's going to be an analog input in this case. So what we are doing here, if you look back at our circuit, our variable resistor will, based on what it is set, as we said it, the voltage here will be somewhere between the VDD and ground, and we will do an analog reading through GP1 and just use that to generate our pulse width modulated signal. So also on the analog selection pins, we have ANS0 is 0, that means GP0 is digital, and ANS1 bit is set to 1, that means GP1 will be used as an analog pin. So the next thing we need to do is to turn on our analog digital converter. AD on is for that bit, and then we need to do something called the channel selection. So this is very specific to this microcontroller, but in every microcontroller you need to do you need to turn on your ADC converter first, and you need to do some sort of channel selection. So that's pretty generic, even though the register names and the bit names could change vastly. Well, in this case, this setting from the datasheet sets our GP1 as the analog input. And yes, this is pretty much all you need to do to get ready for analog digital conversion. Now, the next thing we do is our usual step to just drive our LED. This confusing name address here means analog digital conversion result. So if you remember from our previous video, we were using the duty value here. Now address will be our duty value. The ADC converter on this PIC is 8 bits. So this will change between 0 and 255, and same as our timer. So we will use that analog digital conversion result as our duty cycle basically. And once we do that, we can start the analog conversion by setting go and done bit. So when you set this bit, the microcontroller starts the analog digital conversion and it keeps it high until the conversion is done. So we just put like an empty loop here and wait a little bit until the conversion is complete. And the last bit in our loop is to clear our watchdog timer so it does not reset our processor. Okay, so let's have a quick look at our configuration bits. Our internal oscillator is set as 8 MHz. That puts our processor at 8 MHz. And our watchdog timer is on. Our master clear MCLR pin is set as an input pin, not a reset pin. Otherwise, we would have to pull it up to high with a resistor. And code protection is off. And yeah, we don't have the internal plug enabled on the master clear pin. We're not using that. It's not connected anyways. And that's pretty much it, really. Now let's have a look at our scope to see what kind of signal we are generating. Okay, now if you look at our signal on the scope, it's about 900 Hertz, which is for the given prescaler. That's roughly what it's supposed to be. And it takes about 1.1 milliseconds to complete one cycle. So its period is about that. And if you look at the duty cycle, it's like, yeah, it's like 50%. So what I want to do now is to change the pot a little bit and see how it impacts our PWM signal. Yeah, so this goes to, we can just drive it up very close to 100% duty cycle, and we can bring it down again back to 0%. Yeah, so that's pretty much it. I hope you liked the video, and thanks for watching. If you have any questions, comment down below, and don't forget to have fun.